Herzog here at the University of Calgary. And in 2008, he became a faculty member here in engineering, with an additional adjunct appointment in kinesiology added in 2012. Dr. Federico's research interests include the application of continuum mechanics to biological tissues and complex materials. In the future, he hopes to begin a book project on continuum mechanics and biomechanics. As a fun fact, Salvatore has a great passion for the classics, and last June, he received a Bachelor of Arts in Greek and Roman Studies from the University of Calgary. He is now working towards the Yamaha diploma in modern guitar. When the pandemic is over, he hopes to go back to training regularly. As a reminder, I will first turn it over to Dr. Federico for his presentation, and then we will have a question and answer period to follow. And at that time, I'll remind everyone how to submit a question. And with that, Salvatore, you're welcome to get started.
Okay, thank you, Emily, and good afternoon, HPL. How are you? It's good to see you. I'm ruining all the surprise here. Okay, can this go back? Okay, good afternoon, everyone. So today I'm going to talk a little bit about how it happened that I do biomechanics at all. And so that's why the title is Biomechanicist by Chance. And I will talk a little bit of my personal adventure in continuum biomechanics. So the use of continuum mechanics to describe biological tissues. So why by chance and why Calgary? So in 1999, there was the ISB Congress in Calgary that was organized by Walter. And so my supervisor was supposed to go to Benno's mini symposium on gait and present a paper on gait. And instead it got it completely wrong and went up in Kenmore to the mini symposium organized by Walter on muscle. And so since it was too late to take the car and go back to Banff to the other meeting because it was too much confusion at this point, he decided to stay for the day. And at the end of the day, he was so excited and said, "Oh, if I have a good student, can I send it to you?" And so that's how it happened. That the year after, I came as a visiting student at the HPL. And so I worked with Walter for those 3 months, finished my laurea. So the laurea was the 5-year degree that I did as my first degree that then gave me access to PhD. I wrote my laurea thesis in those months. I got the bulk of it done. And then during the PhD, I came in 2001, 2, and 3, again as a visiting student. And then in 2005, I came to Calgary again as a postdoctoral fellow with Walter. And so the idea was to stay for a couple of years. And those couple of years became 17 years. And I'm still here, and most likely I'm going to stay forever. So yeah, just to give you a little bit of background, this is my hometown, Messina. So that's it's actually seen from the other side with respect to this picture that I have in my background. So this is Messina, where I did my first 2 years in civil engineering. Then I wanted to do mechanical engineering. And so where do you go in mechanical engineering? If you want to do mechanical engineering in Italy, of course you go to Torino, right? So you go to Torino, the Polytechnic. I did all my courses, all my exams in 3rd year. And then I decided it was really very far from Sicily, and it was too far, and I couldn't live so far from Sicily. And so I went back to Sicily, except of course I didn't know I would end up in Canada in some time in my life. But then I came back to Sicily. I completed mechanical engineering in Catania. Then I had my experience in Calgary in the summer of 2000 and finished in October. And then I started my doctorate in structural mechanics, always at the same university. And then I came permanently to Canada in 2005. So I was a postdoc for 3 years with Walter. And then I was a faculty member since 2008 in mechanical engineering. I have a cross appointment in, of course, my appointment is with the CBRE, with the Center for Bioengineering Research and Education. And since 2012, I was invited by Benno to apply for, when Benno was the interim dean, I was invited to apply for an adjunct position, and so I did. And that was granted by Benno. So since then, I'm also adjunct in kinesiology. And so I talk a little bit about the research that I've been doing in the past 17 or so years. 20 years actually, yeah, from 21, my God, 17 since I've been here, but yeah, 21 years. So a lot of my research these days is on the foundations of continuum mechanics, and particularly on the geometrical theory. This is inspired by our god of continuum mechanics here in Calgary, Marcelo, who is also one of the greatest experts on the theory of inhomogeneous materials, and that's one thing that interests me a lot in this period. In particular, I'm interested in solid mechanics, so I work a lot on the theory of elasticity, of porous media, and composite materials, which of course have a lot to do with the modeling of biological tissues. In fact, biomechanics of soft tissues was the first thing that I started to do, and it's still a large part of my group's research. And so we have worked through the years on joint contact mechanics, on cartilage and chondrocyte mechanics, microstructural models of various soft tissues, a lot of cartilage, but also other tissues, and growth and remodeling of biological tissues. This is particularly with my colleague Alfio Grillo, who is now in Torino. So in this case, yes, I will talk. Oh, sorry. This was okay, good. So a little bit of a legend. So when I talk about the research, a single asterisk is a graduate student, a double asterisk is a postdoctoral fellow, and blue are the collaborators from Calgary, orange are from Canada, and green are from elsewhere. Sorry, from the rest of Canada, and green are from elsewhere. So at some point in the middle of the presentation, I will stop and I will ask you if you remember the legend. Okay, good. Okay, so the main motivation originally for my research was articular cartilage. So when my supervisor in Catania, Guido La Rosa, asked Walter what type of projects he had available, Walter said, well, we have projects on muscle mechanics and on cartilage mechanics. And so he sent us some papers. And so I look at the papers and look at the muscle ones and see, oh, wow, that's interesting. Then I look at the cartilage ones and see, oh, that's continuum mechanics. And so I decided to go for cartilage. And that's how I started. And so we know the cartilage is the soft tissue that covers the end of the bones in diarthrodial joints. And so the job of cartilage is to transmit the load from one bone to the other, to redistribute the stress. So as opposed to having a bone-to-bone hard contact, we have a softer contact in which the pressure is distributed over a larger contact area and a ridiculously low friction coefficient that makes our movement smooth when it's healthy. Because when it's not healthy, of course, it doesn't happen. So cartilage is made of a matrix, essentially built of proteoglycans, which are molecules that can hold a lot of water. We will see them in a few slides. And so what you see here stained with this blue stain is the matrix of proteoglycans together with the fluid. Of course, nobody can see them, but there are a lot of ions dissolved in the fluid. What we cannot see with these histological section are the collagen fibers. That's why I depicted them with this cartoon. And so they have a specific arrangement that we will discuss in a second. And these lighter spots here and there in the tissue are the chondrocytes, the cartilage cells. And so because of the morphology that we see in cartilage is traditionally divided in 3 zones. So it has a superficial zone with flat disc-like cells and parallel fibers. It has a middle zone with more or less spherical cells and randomly oriented fibers, and a deep zone with cells that start to be elongated and tend to arrange in stacks of 2 or 3. And the fibers are perpendicular to, well, are parallel to the depth, to the direction of the depth. And of course, this is probably also because the cells tend to stack on top of each other because they tend to be in the interstices between collagen fibers. And the tight mark is the interface between the cartilage and the bone. So there is a little bit of a transition. Of course, it's not an abrupt transition between the 2 tissues, but then under this line, we have the subchondral bone. So the bone that is right below the cartilage layer. So let's start from a little bit of the cells. So this is an electron micrograph of a cell. This is the chondrocyte proper. This is the pericellular matrix, is the modified cartilage matrix that is just around the cell. And then there is the capsule, which is a protective layer that is mainly made of collagen to protect the cells. The cells, of course, like any cells in our body, they synthesize the structural proteins of the cartilage, and they make it essentially alive. And so for the rest, the structural proteins are the collagen fibers and the proteoglycans. So these proteoglycans are, I like to think about those as the bristle brushes to clean the bottles, okay? And they can hold an enormous amount of water. So they can hold up to, in vitro at least, up to 50% their weight in water. And in fact, cartilage is essentially made of water. It's about 80% water. A little bit of proteoglycans, which hold all that great amount of water, and then the rest is collagen. And so what the collagen fibers do is to retain the proteoglycans, keep the proteoglycans in place, and avoid that the tissue swells so much because of osmotic pressure. And the proteoglycan matrix instead retain the fluid, and the fluid has the job of the transport of nutrients, because cartilage is avascular. It has no blood vessels, no lymphatic vessels. So the only way for nutrients to get to the cells is through the motion of the fluid, so the filtration of the fluid through the solid skeleton and through diffusion within the fluid. The proteoglycans are negatively charged when they are in water, and so there are ions that counterbalance the negative charge. There are positive ions that counterbalance the negative charge of the proteoglycans, and whereas the collagen fibers are electrically neutral. So what happens is that these electromechanical effect gives cartilage its stiffness in compression. So it's together is the fluid that is water, so it's nearly incompressible, and so it gives a lot of stiffness in compression, and also the fact that the fluid is trapped by the proteoglycans, whereas the collagen fibers resist in shear and tension. Okay, for the solid fluid interaction, instead, the collagen fibers deviate the flow of the fluid because they are a physical impediment to the flow of the fluid, and the proteoglycan matrix, with all these very small interstices between the lateral branches of the proteoglycans, give the bulk of the fluid, of the resistance to fluid flow. So there are a lot of tests that can be done on cartilage. Very classical tests are the confined compression one, for example. So we have a rigid chamber, where rigid means orders of magnitude stiffer than cartilage. So we put cartilage in a chamber. We use a porous filter so that the fluid can only exudate through the porous filter, and we compress. And so we can measure the properties of the tissue in one direction, the direction of compression. And so we can look at the location dependence of the material properties. So we look at inhomogeneity of the tissue. And so, for example, based on confined compression tests and on uniaxial tests in one direction, it was possible to measure the stiffness of cartilage, which is very small in the surface, and then it becomes higher and higher as we go down towards the interface with the bone. Whereas the permeability increases from the interface with the bone, and then at some point it crashes down and decreases again, which is fairly counterintuitive, and we will talk about this later. So cartilage is also a tissue that undergoes large deformations, for example, as opposed to bone, which doesn't undergo large deformations, because if a bone undergoes large deformations, it's a very bad thing because it has broken a lot before, because it's a very rigid, it's a very stiff tissue. So cartilage is a softer, much softer tissue, so it can undergo large deformations, and so the stress and strain curve is evidently very nonlinear. The permeability is also deformation dependent, because the more we compress the tissue, the more the pores become smaller, and so the greater the difficulty for the fluid to flow, so the smaller the permeability. And another test that we do is the unconfined compression. So we have two rigid plates and the fluid connects today through the lateral surface. And so in this case, we can measure properties in different directions. So we can measure properties in the axial direction, so the direction of the depth, and the transverse direction. So we can look at the anisotropy of the tissue, the directionality of the material properties. Okay, so looking at cartilage from the point of view of a continuum mechanist, it is a multi-phasic system made of a solid, of a fluid, and dissolved ions. It's a microstructured tissue, so it has cells, it has proteoglycans, it has collagen fibers, and it has the fluid. It's anisotropic, so the properties depend on direction. It's inhomogeneous, so the properties depend on location as well. And it's highly nonlinear. So when it undergoes large deformations, the properties are no longer, so the material properties are no longer constants, and so they change with deformation. So the things that initially I, and then together with my group, have done in the past 20 years have been quantum mechanics, microstructural models of linear, nonlinear elasticity and permeability, working towards a comprehensive microstructural model that also included diffusivity, for example, and then growth and remodeling. Those are the main topics I'm going to talk about today. So with quantum mechanics, this was the very first work that I did with Walter. So this was my laureate thesis back in 2000. So we were studying different configurations of cartilage. So based on experimental data, how normal early osteoarthritic and late osteoarthritic cartilage behave when we have a contact problem between two ideally spherical surfaces. And the goal was also to look at what were the best possible boundary conditions for the fluid flow at the surface. So do we completely seal the surface and not allow fluid flow, or do we allow an exchange of fluid between the two surfaces, or do we allow a proportional exchange of fluid? So that was essentially the work of my thesis. This problem in quantum mechanics continued later with Sang-Yu Han. There was a student with Walter and Marcelo, and now he's a senior researcher back in Korea at the Korean Institute of Industrial Technology. And so we were studying on a real joint, on a real feline joint with the patella and femur. This joint was scanned precisely to get the exact geometry. And then we worked on finite element simulations to show the effect of misalignment on the pressure distribution. And so we see that if this is the reference position of the healthy joint, if there is a transected ligament, for example, due to an injury or due to an experimental protocol, then of course, regions of cartilage that used to be loaded are no longer loaded, and regions that were weakly loaded, now they get very loaded. And so that caused that in the protocol, in fact, causes osteoarthritis to arise. And then a large part of what I did in my PhD thesis was a microstructural model of articular cartilage. So the idea was that a phenomenological model is a black box with a certain set of parameters that we have to curve fit to experiments, whereas a microstructural model has keeps track of the role of the various structural elements within the tissue, of their spatial organization, from which the anisotropy and the inhomogeneity arise. And so we went for a microstructural approach, and the main thing that I worked on was to model the orientation, the spatial orientation of the collagen fibers and the effect that this spatial orientation has on the material properties. And so this yellow thing here, this yellow tube represents roughly a fiber. This was a drawing that Jorge did for me many, many years ago. Some of you, the ones of you that have been here long enough know Jorge. And so the blue one, the blue cylinder, is the tangent to that fiber at that point. So I look at the vector M that identifies that direction. I can express the vector as a colatitude angle. So this angle here will be the latitude. So the complement to 90 degrees will be with the colatitude. And then I look at the longitude, and then I can use these two parameters to describe a probability distribution to find a fiber in a certain direction M. And so when I average a certain material property over all directions in space, I can get the overall effect of a certain distribution of fibers. So let's look for a moment at what linear and nonlinear elasticity mean. So most bodies have an elastic behavior. Not all bodies have an elastic behavior. Sometimes it's more complex, it's viscoelastic, or it's plastic, or is viscoplastic, but a lot of materials on a short time scale behave fairly elastically. So a mathematically elastic body recovers the original configuration when the load is removed. More precisely, it is completely insensitive to deformation rate. So the stress exclusively depends on deformation. So that's the definition of an elastic body. So if you look at the discrete example, for example, a spring and mass, so the energy will be a function of the position, the force will be a function of, will be the first derivative of the energy, and the stiffness will be the second derivative of the energy. If the system is a linear mass spring system, then the energy is quadratic, the force is linear, and the stiffness is a constant. So for a linear elastic material, we have the stiffness, which is given by the elasticity tensor, which is a constant. So this was the, I will not go into the details, but we try to reproduce the curve that I showed you before of the uniaxial stiffness of cartilage in the axial direction. And with this model, we were able to reproduce relatively closely that curve, given the arrangement of the collagen fibers. But that doesn't really work. It looks like it worked, but it doesn't really work, and I will tell you why in a moment. We also used a similar model to study together with Sang-Yuhan again, a microstructural model for the a two-scale model for the cells. So we were deforming a macroscopic sample and then taking the deformations at each point on the axis to study a certain cell. So apply that deformation as a boundary condition on a cell model to see the to study the formation of the cells. However, we eventually with Walter decided that it was about time to move to a nonlinear model, and you know, as much as isotropic and inhomogeneous is nice, that's not enough. It has to be a nonlinear model. So rather than taking averages of the elasticity tensor, which is what we would do for a linear material, we take the average of the elastic energy. So this is the overall elastic energy. This will be the contribution of the isotropic protoglycan matrix, and this will be the contribution of the collagen fibers. So this is the probability distribution to find the collagen in direction M, and this is an energy that depends on the deformation. This is the Ricochet-Green deformation is a very fundamental measure of deformation in a material, and this is the structure tensor, so which is a tensor that takes into account the direction of the fibers. And we also have a finite element implementation that we developed with Christian Gasser from the KTH in Stockholm in 2010. And so we use the method of the spherical design. So we have an integral of this type over the sphere that represents all possible directions in space. So we approximate it with a set of conveniently chosen points on the sphere. And so we do a summation rather than an integral. And after that, with one of my students, Kotai Blashlamun, which is now a postdoc in chemical engineering here in Calgary, we worked on rapid integration methods for cases in which the fibers are on orientation. Another thing that we did on this front in nonlinear elasticity of soft tissues was a damage model, and actually a model for the recruitment and failure of the fibrils in a collagen fiber. So a collagen fiber is made of several fibrils, and not all of them are have the same undulation in the reference configuration. So some are a little bit more straight, some are a little bit wavy, and so as we pull, some of them start to be completely stretched when the others still are wavy. And so some fail first and some fail later when we go into a stretch that is such that it damages a fiber. And so with this model, we were able to reproduce the behavior of a a tendon. So that's an experimental, this is an experimental curve from a real tendon that is pulled to damage. You can see the classical J curve of a lot of soft tissues when they are subjected to tension. So there is a nonlinear region at the beginning, it's called the toe region. That's exactly when we are recruiting slowly the collagen fibrils inside each fiber. And then when all the fibers are recruited, actually they respond fairly linearly for a good interval of deformations. And then they start to fail. And so the load decreases dramatically, and then the tendon can no longer bear load. And so these are subsequent refining of the same, of an initial mesh. This is a very coarse mesh with 48 elements, but already at about 1100 elements, we got convergence. So this is 6400 elements, and you see that's the black line, and that's pretty much when we got convergence. Okay, so this is a work that we did more recently with Enquan, who was a postdoctoral with Walter and co-supervised also by me, and now is in Finland with our colleague Rami Korhonen. And so this was a work on the a nonlinear poroviscoelastic model of cartilage, and a comparison with experimental data. So the model was poroviscoelastic. It was a classical model, but the collagen fibers were viscoelastic. So we allowed a dependence on the deformation rate for the collagen fibers. And so this is what happens to a crack when we have a cracked tissue and we compress it. We see how the crack deforms. So the crack tends to close in the deep zone and tends to remain open in the superficial zone, which is exactly what was observed in mature cartilage, and whereas the crack tends to remain open in immature cartilage, and this was also captured by the model. Okay, so then there was a beautiful question that I was asked back in 2006. And so the question was, after an HPL seminar, that's one of the many reasons why I love HPL seminars. And so I was presenting my elasticity model. And so the question was, but having modeled the effect of fibers on elasticity, why haven't you thought about the possible effect on fluid flow? And so for this, I would like to thank Vincent von Charner that asked me that question and started an entire stream of research for me and for Walter's group and for my group. And so I was very intrigued by that question, and so I started to think about how to work cartilage permeability out. So let me quickly show you what this is about. So permeability is the propensity of a porous medium to allow a flow to pass through it. So if I have my usual rigid plates and I have two porous filters here, and I apply a gradient of pressure, so I have a higher pressure here, lower pressure here, the fluid wants to go to the lower pressure, and so it passes, and there is a flow, so there is a volume per unit time that passes through the second filter. So in a discrete system, what I do is I take the ratio between the two pressures, the difference of pressure and the difference in position, and I measure the fluid flow, and I will find that it's proportional to a constant K that is called exactly the permeability. For a continuum, this permeability is a tensor, in fact, because the gradient of the pressure is a vector. It's a covector, actually, but that's a different story. So the permeability is a tensor. And so the objective of my studies was to find the permeability tensor of a tissue like cartilage that has collagen fibers distributed in the interesting way that we've seen before. And so what I thought was, okay, we have two families of pores. We have microscopic pores that are those in the interstices between the glycosaminoglycans of the proteoglycans, and we have mesoscopic pores that are the interstices between the fibers. So what I did was, okay, let's take a cylinder, a representative element of volume, cylindrical element with a fiber in the middle, and a jacket of proteoglycans and water around, oriented in a certain direction M, and let's see what happens with this element of volume. Then, to get the overall behavior of the tissue, we need to average overall possible directions. And so this is what we did. This is the referential element of volume. We have our probability distribution. We applied the pressure gradient. We solved for these element of volume and found the permeability. One thing that I would like to say is that I was lazy enough not to actually solve the problem. In fact, I thought, well, the permeability problem is exactly the same as the electric permeability problem. So if I find a solution for the electric material, if I have the electric material made of a cylinder and then another cylinder with different dielectric properties, if I find a solution for that, I can just apply the solution to my water permeability problem. And that was the case. In fact, I used a solution by Landau and Lifshitz for the electrics, and I just changed literally the names of the variables, and I got the solution for our problem. Then I averaged and got the permeability of cartilage. This is the graph that I showed you before, the experiments of Marudas and Burlow. So they thought, okay, these catastrophe here in the permeability happens probably because the collagen fibers are providing a further impediment to fluid flow, and that's why the permeability decreases rather than increasing again, because the density of proteoglycans actually decreases. So there are less proteoglycans, there are bigger pores, so that means the permeability should be higher, right? But that was not the case. And so Marudas and Burlow inferred that probably it was because of the collagen fibers in this direction that the fluid flow in the orthogonal direction was impeded. And in fact, by using this model, we were able to reproduce exactly the same curve just by imposing, with little parameter adjustment, but just by imposing that the collagen fibers be oriented as in the actual tissue. Okay, so now we have a comprehensive nonlinear model. So we have, we account for the compaction limit, for the statistical fiber orientation, the nonlinear elastic behavior, large deformation effect on permeability, and we also have a full nonlinear, finite element implementation for these classes of models. So more recently, we have worked on refining these models with Moss and Maleki. There was a postdoc with me and Walter, and Kotaiba Shlamund, there was the same PhD student I was talking about. And so actually there is one thing that the large deformation permeability model could not do, and it was to capture these in a confined compression test, was not able to capture the behavior of the ratio between the axial and the transverse permeability, because it was predicting that it would decrease, whereas actually in experiments it increases. And so with this new model in which we also account for the distortion of the representative element of volume, we can capture that behavior. Then with Kotaiba, we also did a model of diffusivity. And so with this model, we can actually predict the diffusivity of spherical molecules pretty well. So we can predict what the effective permeability of cartilage would be as a function of the hydrodynamic radius of the molecule. If you see these small points here, it doesn't quite work for linear molecules, because linear molecules can reptate through the collagen fibers, and so they diffuse better than spherical molecules. So we need to do a lot more work to address that type of molecule. This is a work that we also did with Walter, in collaboration with Walter's group, and we used the beautiful microscopy facility in the Human Performance Lab. And so Kotaiba was bleaching, was using the fluorescence recovery after photo bleaching. So he was bleaching, was staining the tissue, bleaching it with the laser of the confocal microscope, and then watching the recovery, studying the recovery of the molecules from the non-bleached area that were diffusing into the bleach area. And that was, so the circular region became slowly an elliptical region, meaning that the diffusivity in the direction of the semi-axis of this ellipse were different. And so we were able to measure the anisotropy of the diffusivity. And so this was paired with a numerical model that was able to evaluate the diffusivity, and particularly the anisotropy and the direction of anisotropy of the diffusivity. Other things that we do also in the spare time is working on some topics in finite elements, also because they are particularly useful for modeling biological tissues in, for example, in Abacus. Abacus is a fairly popular software for a lot of studies in biomechanics. And so with some of my trainees, we were doing, showing how to find exactly the elasticity tensor that has to be used in the numerical implementation of a user material. So Abacus wants a precise expression, which is not explained anywhere in the Abacus manual. They just say, yeah, use this tensor, but they don't quite explain how to find that tensor. And so we did so for shell elements, which, for example, we used for blood vessels. This was in collaboration with Chiara Bellini, which is now a professor at Northeastern University in Boston. And this is a study with Samer Adib that was also Walter's postdoc when I was a postdoc, and has been 6 months before me became professor in Edmonton, and Medal Palizzi is his a PhD student. So we did this for raid materials and solid elements. Okay, I will talk just a little bit on growth and remodeling. This is work that has been inspired by Marcelo, who has this beautiful and very highly cited paper on growth mechanics together with the late Professor Mojan. And this was published in 2000, exactly when I came as a visiting student the first time. And so that's when I got to read it. I think I got to read it the first time in 2001, actually. And then this inspired the laurea thesis of my alter ego, Alfio Grillo. So this is Alfio in a picture of some years ago. And Alfio, like all biological systems, also grows and remodels. And in fact, this was Alfio when he graduated PhD. This was Alfio a couple of years ago. So you can see there was a reference configuration. There is a current configuration. There has been some remodeling, but I cannot say anything because this is me in front of kinesiology B222, which is just a few steps out of the seminar room. This was me with the hair, and this hair has remodeled into a very aerodynamic skull surface here that you can see. So I cannot really talk about remodeling. Anyway, so I'm going to talk in particular about a work on remodeling of cartilage, which has been inspired by Professor Giaguinta. So Professor Giaguinta was my professor of solid state physics and structural matter in Catania, and was Alfio's PhD supervisor. This picture was taken by another PhD student, Gian Domenico. And in this picture, Professor Giaguinta is standing on one of his desks in his office. He was putting a painting on the wall. So Professor Giaguinta had this idea once in 2004. He was looking at the curve that I showed him for modeling the probability distribution of the fibers. So I had 0 angle here, then the curve went up to 90 degrees. And so here I have a peak at 90 degrees, here I have a peak at 0 for the orientation of the fibers. And then he looked at the picture and said, oh, but wait a moment, this must be a structural phase transition. This must be a structural phase transition. So at the moment, we really didn't understand what Professor Giaguinta was talking about. And he said, we should use a Ginzburg-Landau energy with 2 minima. And so the idea sank for a long time until Alfio started to work again on it. And I worked together with him. And so we used the Ginzburg-Landau energy with 2 minima, 1 at 0 and 1 at pi over 2 at 90 degrees. And so we said, okay, can we use this energy, start with a random distribution of fibers and see if cartilage evolves into real cartilage. So we have a fake cartilage with random fibers, which actually is not particularly fake. It's immature cartilage. Initially, immature cartilage, the fibers are very random. Then they start to get the familiar orientation when the tissue matures. And so the answer is yes. It was actually possible. It was actually possible to model the orientation, the real orientation of fibers, both in the healthy tissue and in an osteoarthritic tissue. And this was compared against experimental values found in an earlier work by another group. Another work on remodeling was done with Amira Mezzadeh, that was one of my other PhD students, with Alfio and Marcelo as well. And here we were using two families of fibers to model a simplified blood vessel. And so we were able, with the so the remodeling parameter here was the orientation of the fiber again. So we gave an initial orientation, and then we let the model evolve. And so the collagen fibers slowly changed orientation through the thickness of the vessel. So the change in orientation was different at every radius in the vessel, and that was to minimize the stresses within the tissue. And in fact, the distribution of stress that we found in the vessel was very closely comparable with the one observed experimentally. One other work that I've done together with Marcelo lately was with our student Ivan Defaz. So Ivan studied the propagation of solitary waves in elastic dielectric tubes. It was a lot of fun. I hadn't done electromagnetism in a long time, so I had to review a lot of my electromagnetism. And so we solved the problem. This is the propagation of the radial displacement. So the bulge that is created in the vessel as the solitary wave travels through the tube. Okay, so at the moment, just to wrap up a little bit, we have an elasticity and permeability model that are widely used. There are several groups around the world that use our models or models that are very similar to ours. We have growth and remodeling models that can capture fiber arrangement in biological tissues. And so for the future, one thing that I would continue to like to do in biomechanics would be to study the interaction between material properties and osteoarthritis and the disease and the evolution of the disease. And so hopefully in the long run, most likely not from my group, but from other groups that use our results, there will be some application directly from the basic science results that we try to obtain to more clinical applications. So at the end, I would like to acknowledge all the colleagues and friends that have helped in all these works. Samer Adib, Marcelo, Epstein here in Calgary, Christian Gasser in Stockholm, Professor Giaquinta in Catania, Alfio Grillo in Catania. Originally, we were students together in Catania. That's how we met. And now in Torino, Walter, of course, and Roberto Martinuzzi in mechanical engineering in Calgary. We also did one of the permeability works together. And I had a lot of work getting my program started originally with the Alberta Ingenuity, then Alberta Innovates new faculty program. And of course, I am supported by NSERC, without which in the past 10 years after the Alberta Innovates was depleted, I couldn't have done absolutely anything. And as I've been done in the past 5 or so years, I'd like to dedicate this talk again to Professor Giaquinta. So this is a picture taken 2 weeks before he passed away in 2006. We were in Catania. This was the 28th of July. This was Leo. So Leo was 4 years old, and Luca was just 7 months old. And now Luca is quite bigger than Leo was in this picture. And this was the last time we met, and it was very sad. And so I'll go ahead, otherwise I start to cry. And thanks so much for your attention. And if you have any questions, I'll be most happy to try to answer.
Thank you, Salvatore, for that great presentation. At this time, I would like to encourage everyone in the audience to turn on their video camera if they're comfortable to allow for a better discussion. And Salvatore, if you were willing to stop sharing your screen, that's perfect. To ask a question, you can use the raise hand function under reactions, which is on the bottom of your Zoom screen, and I will call on individuals from there. And if you're unable to use the raise hand function, you're welcome to type your question in the chat box as well. Great. Amin,
No
would you like to
questions.
ask
So
a
I
question?
either bored you to death or I was too clear. No. Oh, Amin, thanks. Amin, please go ahead.
Hi, Salvatore. Thank you for your presentation.
Thanks, Amin.
We have researchers who study knee joint like at tissue level. They study the whole knee joint, including femur, tibia, cartilage, meniscus. In those models, they just easily go with a single phase elastic cartilage. And when they add the fluid phase, then they start calling our model is like advanced cartilage model, right? They don't consider like the effect of collagen fiber or like anisotropy, different like permeability in different directions. I just want to know your comment about that. Is there like what would be the problem with those models in your opinion?
Okay, so that is a very good question. Thank you. I mean, in fact, I had discussions with Walter about this just a few days ago. I recently rejected a manuscript that I was reviewing because the authors wanted to study the dynamic properties of cartilage with a single phase model that was purely elastic. So an elastic model, if you load it instantaneously, if you load it in a few seconds, or if you load it in the age of the universe, which is 13 something billion years, it doesn't make any difference because by definition, the deformation rate is irrelevant. So this was very problematic in this manuscript because they wanted to study the dynamic properties of the tissue. So if you study at the tissue level, I think that these days it's just not possible to think of a model that is not microstructural these days because we have the computational power to do that. The models are out there. It's not that it's just my model. There are a lot of microstructural models that are equally good for different things, and they can address different things in different ways. There are a lot of models available, so there is really no excuse if one is interested in studying the properties of the tissue specifically. So, example, taking the tissue and doing comparing with the experimental results on a tissue sample. Now, when it comes to an entire joint, I understand that there has to be some simplification, right? So I still think that a single phase elastic model just shouldn't be there. There should be no single phase elastic model because there would be no time dependence of the model whatsoever. So even if it's an entire joint model in which the cartilage deforms relatively little, but still there is a dynamic behavior that cannot be captured by the single phase model. So to me, the bare minimum, the real bare minimum, it's still in the 1976 Torzilli and Mao paper or 1980 Mao et al. Paper. So that is the biphasic linear elastic model. That's the bare minimum. And 1976 is when I was born. So that's why I'm particularly fond of that paper. No, it's as old as I. So there is no excuse. There is no excuse to use a single phase model. Single phase and viscoelastic, maybe. Okay, sure. Single phase and viscoelastic, we can talk. But single phase elastic, in no instance in 2021 can be acceptable, I think. Sorry if I sound particularly hypercritical of some colleagues that insist with the linear elastic monophasic model, but it's just wrong.
Thank you.
Thanks, Evan.
Robert, would you like to ask your question?
Yeah, I would. Thank you, Salvatore.
Hey Rob, good to see you. How are you?
Nice. I'm well, thank you. It's morning here.
Yes,
I'm wondering about the presence of cross linkages,
yes,
particularly perhaps in the mid region where the collagen fibers are sort of crossing each other. And down in the deep region and in the surface region, they seem to be uniaxial, which implies a sort of a uniaxial action. Are we aware of greater levels of cross linkages in the mid region, and does that stop it? Or would cross linkages stop it being uniaxial and make it act more like a matrix?
So that is also another great point. And in fact, the cross linkage has been studied for quite a long time. I think one of the first one to model a cross linkage of fibers was in fact Leping. Was Leping Li in his model of, I don't remember if it was the 99 or the 2001, but Leping used to, so Leping had two classes of models. He initially had the finite element model with the solid elements representing the matrix, and then he added springs connecting the nodes. He had nonlinear springs. And so he had springs in all directions. So in all the three directions. And that in fact was also simulating the cross linkages. So in the deep zone, he had weaker springs in the transverse direction and stronger springs in the axial direction. And so that was simulating the cross linkages. Another way in which this can be done with the type of models that we use, for example, with the directional averaging, could be to use the famous or infamous, depending on the point of view, invariant I8. So the I8 invariant, and this is something on which Enquan has asked me to work for a long time, but Enquan and Scott and I have a discussion about this every once in a while and then never start to do anything because we are all too busy. But the idea would be if I have two fibers, so if I have one fiber, I can establish some invariance of the deformation. So for example, if I have a rotation about this fiber, then nothing changes. So there are some things that are invariant about rotations, under rotations about the fiber. And so when I have two fibers, I can have a term that describes the interaction between the two fibers. And so if my energy depends on one of these invariants, like this I8 invariant I'm talking about, then that can be used as an interaction term between the fibers. So that can mathematically represent a cross linkage between fibers. So yes, there is a way to do it. And I would have liked to do it, but I never had the time. So to the best of my knowledge, that would be one of the ways.
Yeah.
HPL Calgary, I see that you have a raised hand.
Oh, go ahead. Can you hear me, Salvatore?
Yes, I can hear you. Is that hard?
Okay. So in the beginning, you showed this figure.
Yes.
Where you had stress or pressure on the y-axis and radius on the x-axis, and you had these curves that showed how the pressure changed as a function of the radius for healthy, old, and early OA tissue.
Oh, yes. Okay. Give me just a second. I'll get there.
What was, yeah, I mean, you don't have to pull it up. What was the radius? Was that just the size of the
contact area?
The contact area that you manipulated with some kind of.
As soon as you hit zero stress, that's where the contact area ends.
Oh, okay. All right. Oh, okay. All right. I get it now. I thought you were using different size of indenters to test the cartilage.
No, in fact, the size was exactly the same, but the contact area was different because the properties of the tissue were different because of the disease.
Okay.
Sorry, I went too fast on that. Sorry.
No, that makes sense. Why is it that you have normal cartilage, and then for early OA, the stresses tend to be lower, and then for old OA, the stresses are higher than normal?
Yes. So that is because not only the sorry, I'm trying to watch at you and to also watch at the figure. So can I pull the figure out for a moment?
Yeah.
Okay. Not that is incredibly important, but let's pull it. No, sorry, that's not this one. So here we go. Okay. So not only the elastic properties become different, but so what we simulated was in early OA, we increased the thickness of the tissue because it actually swells more. Because what happens is that the superficial collagen start to disrupt. And so the collagen is no longer able to keep the protoglycans from expanding because of the osmotic pressure. And so the thickness of the tissue increases and the permeability increases, becomes about twice as big, twice as large. And so the permeability is larger and the thickness is larger. And that's why the pressure is smaller, because overall the tissue is softer. But then when the tissue is very eroded, the thickness is smaller, and that's why you have a higher stress. Of course, this is in the nice and simplistic world of numerical simulations, right? But that gave the idea of what happens in reality, because we try to.
Can I just add something, Salvatore?
Walter, please.
This is not only in the simplistic way of modeling. If you remember that the parameters that you actually used for input were actually measured on cat ACL transactions. So,
absolutely, yes.
This is the material properties are based on actual data.
Yes, no, and this is not what I meant, Walter. Sorry, I didn't explain myself well when I was talking about the magical world of simulations.
I didn't say that for you, Salvatore. I really said that more as an explanation to the other people, because other people might think, why should cartilage get thicker? Why should it get softer in early OA? But that is what happens in many of the animal models, and it seems that's what happens in humans if you, if you have a post-traumatic scenario.
And in fact, thanks, Walter. And in fact, that swelling is due to the fact that the collagen fibers no longer retain the protoglycans as well as they did before. And that's why the tissue becomes softer. But then when the tissue gets eroded, it becomes thinner. And that's why it becomes stiffer and you get higher stresses. So that was the rationale. Of course, these curves are perfectly, nicely smooth because we just had two perfect spheres that were in contact. That was the magical world of the simulations that I was talking about. So we just have perfect spheres with different material properties. But this captured the idea of the material property, of the change in material properties that occurs in early and late osteoarthritis.
What happens to the? Yeah. Okay. Thanks. That's interesting. So what happens to the? What happens to the collagen fibers themselves? Do they become old? Do they become more cross-linked?
They break.
They become broken, damaged?
They just break. They break, they fail.
Break. Okay.
They start to fail. They start to degrade. They start to degrade. And I believe, and Walter can correct me on this one if I say something completely wrong, but it starts to be, it's a mechanical and also an enzymatic degradation. So they start to degrade chemically. So it's the structure is really disrupted. And so they, at some point, they break at much lower stresses than they would when they are healthy.
Got it. Thanks.
Thank you.
Siska, please go ahead.
Thanks. Hi, that was really nice. Really nice to see you.
Thanks.
I was just wondering about the cross-linking. What is the functional reason that there is this reduced permeability and the cross-linking at the middle region? Or why?
Okay, so I think we're talking about two different things. So in any of the model that I showed, there was no cross-linking. I didn't model the cross-linking. So what I did, and let me show you the plot. Let me look for it. There we go. So what I meant is that the collagen here. Oh, what did I do? Okay, sorry, 23. I know it's 23, sorry. Where is it? Come on. Here. So what I meant is that Marudas and Bolo were trying to measure permeability in the axial direction. So what they did, they used a microtome and they cut slices of cartilage parallel to the surface. So they were putting then each slide into a machine, and they were making water filter. Ridiculously difficult experiment. In fact, we tried to do something more complicated than this, and it failed miserably. So it's very difficult to do these experiments. In fact, in a first study, the curve that they got was monotonic. So the permeability was monotonically increasing, but they said, okay, we would like to warn the reader that actually we couldn't measure permeability in the very superficial layer because we couldn't get a good cut. So they did another paper, this one, in which they actually could get a good cut. They used a beta microtome, and so they found that the permeability in the superficial zone was actually much smaller than what they were expecting. They were expecting it to be out here, and they found it to be here. And that was because they were measuring in this direction, and they said, okay, the only thing that can make the permeability decrease so much could be the collagen fibers, because they are against the fluid flow. Whereas in the deep zone, the collagen fibers are in the same sense as the fluid flow. So it's much easier for the fluid to flow, although the proteoglycans here are much denser, and so the pores are smaller. So the collagen fibers here don't give they don't disturb the flow very much, but they disturb the flow a lot here. So here you would be expecting a much higher permeability, but it's much lower because of the presence of the collagen. Did I answer your question, Siska?
Yeah, that makes it more clear. One thing I was also wondering is why it is like that, or what would be the reason?
Okay.
Functionally,
so,
yeah.
Functionally, one reason could be that cartilage wants to be sealed. The fluid doesn't want to exudate much or very fast from the surface. Probably nature wants that the fluid doesn't go very fast. Otherwise, if we stand, forget our intervertebral discs, but think about the knee. No, we stand the entire day. We don't want all the water to get out, right? So probably we want it to be very, very, very slow. That's why the permeability has to be lower there. In fact, I had discussions with Nigel Shrive some time ago, and Nigel has always modeled the surface of cartilage sealed, completely sealed. He says, to me that is very, very little flow. So to me, that's practically zero flow. So he just models it sealed. So probably the idea is not to get the fluid out very easily.
Thank you.
Thank you.
Reza, please ask your question.
Yeah, thank you so much. Very nice talk.
Thanks,
Federico. Very interesting constitutive model you have in 2010 with Dr. Gasser, and with combination of collagens and proteoglycan. And one slide that you showed about the glycosaminoglycan, and they negatively charged and they absorb water.
Yes.
I was wondering how we can include this in our constitutive model.
Okay, so actually none of the models that I showed are including the ionic phase. So actually all the models that I have worked on are biphasic, so they have only fluid and solid. The ionic phase can be included. There are a lot of triphasic models with ionic phase. And so what happens is that the ionic phase adds a term to the hydrostatic pressure. So there is an extra hydrostatic pressure that comes from the osmotic pressure due to the ionic phase. But these are even old. There are old papers that do this. There is Mao and Lai, I think 1986, the first one. I think, if I'm not wrong, is Mao and Lai 1986. I have to check. I haven't looked at those in a long time. But these can be These can be modeled also constitutively. There are constitutive models of those that go with volumetric deformation. So you get essentially an extra term. You get an extra term in your stress. So you have your solid stress, then you have the hydrostatic pressure, which is the Lagrange multiplier of the incompressibility of the solid and the fluid separately, and then you have the additional osmotic pressure term.
Yeah.
So those can be found in the literature. I can point you to some of the most important references. I have to look them up myself because I don't remember them on top of my head.
Yeah, thank you so much. There is one more question I have. When the tissue or the material that we have is really soft, then the constitutive model is more advanced. And then we have complex geometry like cartilage that we extract and segment from MRI images. Then we want to combine these and apply forces like running forces. Then we see divergence, especially in abacus or finite element software. It's really hard to converge these models. What suggestion, recommendation do you have for?
So this follows up a little bit the point that Amin raised earlier. So when you want to have a full joint model, as of today, we need to still renounce to something. Although the computational power that we have today is orders of magnitude the computational power that we had 20 years ago, it's still not enough. If I need to model an entire leg with all the muscles and the ligaments, and then I have to also model 1 million nodes for the cartilage layers in the knee, that starts to become tough. Even to simulate a second of activity, right? So we need to make compromises. Again, I still think that biphasic elastic is okay. Even isotropic, possibly nonlinear, would be okay. So there should be a compromise and see where we can stop. I know that there are models that are interested really in pretty much in the muscle. So they do force sharing between the muscles. So they want to evaluate which muscle is doing what at which time. And so probably in those cases, going really easy on the cartilage is okay, because you're not really interested. You're not even close to getting the stresses in cartilage because you don't really care. Even if your stresses in the cartilage are completely wrong, it doesn't change the load that the muscle is going to bear, right?
Yeah.
So it's a trade-off between, and it depends what you're interested in. So using a supercharged model for an entire joint is just too much. Maybe in 50 years we would laugh at this and say, oh, of course you can do it. And we could do 75% of the brain too, the same model. but still not today.
Yeah, sure. Thank you so much.
Thanks.
Brent, in the seminar room, would you like to ask your question?
Yeah. I thought of another question when you showed that figure with all the different fibers with the fiber direction as a function of depth. So I find it fascinating that you have come up with some growth and remodeling algorithm.
Yes.
Where you just start with a random distribution of fibers.
Yes.
And then you're able to basically get this kind of distribution.
Yes.
So did you say that the law sort of governing the growth and remodeling, it's something that tries to minimize the stress distribution? Is that what it does?
So practically, okay. So there are two possible approaches to growth and remodeling. One is the one that is used by Marcelo and is based on internal parameters. So there are internal variables, and you write an evolution law for the internal variables. So in this case, for example, the internal variable will be the direction of the fiber. Okay. then there is the approach that is due to Gurtin. And so we have used this approach, for example, with internal variables here in this work. Okay. Whereas in this work that we did with Alfio, this is also with Alfio, by the way, but in this work that we did with Alfio instead, only with Alfio's group, we use Gurtin's approach. So Gurtin actually is one of the fathers of thermodynamics with internal variables. But then at some point in his life, he decided, no, I don't like this anymore. So rather than using internal variables, the fiber direction, which is the remodeling parameter, is treated as an additional degree of freedom. So it's an additional kinematical variable, not an internal variable that I have to treat with some evolution law. I treat it as a kinematical variable, exactly as I treat the velocity of the continuum. Now the velocity field is a kinematical variable. Okay, the time derivative of the direction of the angle, of the fiber direction is a kinematical variable. And so I write a balance equation. There will be, if it's a kinematical variable, there will be a force that acts on it. You know, a velocity is an object on which forces act to make power. No, a force is a linear operator on a force, on a velocity. So a force takes a velocity and gives you power. Like a current takes a difference of potential and gives you power. It's the same thing. In the same way, there will be some conjugated force that acts on the time derivative of the fiber direction, and then you have a balance of that force, exactly as you have a balance of the regular forces that we see in macroscopic. So that's based on that point of view. There are several ways to do it. Yeah.
It's way over my head, but like, I guess what I'm wondering is, clearly the fiber direction determines in part the material property of the
Yes.
of the element or whatever. But what I'm wondering is, when you also start with this random distribution of fiber directions, do you also have to do things like, model the microporous structure differently in the superficial zone than you do in the deep zone? Do you have to model the calcified cartilage, or do you just?
Okay. So this was taken into account through the permeability model. So the permeability model at each instant of time takes the fiber direction and gives you the local permeability. That's the idea. So we were not specifically modeling the pore. We were using the permeability model that I showed you earlier to evaluate the permeability at each instant of time. The thing is that at each instant of time, the fiber is reorienting a little bit because the tissue is deforming, and a little bit because it has its own degree of freedom and wants to reorient to follow its balance equation. That's the idea. Am I giving the idea?
It'd be cool to like get some imaging on some, maybe an animal model or something, where they're able to you're able to grow an animal or take them through development, but maybe unload a limb or something and see if the cartilage kind of stays randomly distributed, or if it orients itself the way that articular cartilage tends to be.
So if he stays like that, for example, in the absence of gravity or something.
Yeah.
Okay. Yeah, it'd be cool. That'd be interesting. Yeah.
Thanks.
Thank you. Thanks, Brent. Thanks.
Walter, please go ahead.
Very much. That was very nice, Salvatore. And maybe the fun fact that I would have said about Salvatore is that he came in 2000 for 3 months, and that was the basis for his master's degree. Then he came summers for 2 months, so a total of 6 months, and that was the basis of his PhD. So I always think of him as getting his master's and PhD in a total of 9 months. I have a couple of questions, but I see Amin is behind me, so maybe you can ask them, go through them relatively quickly, Salvatore. The first question I have is, you use elasticity, viscosity in your matrix. Do you think that's essential? Because I know that some people consider the matrix as elastic, but you have it as viscoelastic. Do you think that's an essential component for the predictions that you make?
So, thanks, Walter. That has been that has been an argument for a long time, and in fact, I have to say the only model in which I used the viscoelastic fibers was this one with Enquan.
Mm-hmm.
Was this one with Enquan, because Enquan was so this is the work that he started to do when he started to work with Rami, and so Rami had this model with the viscoelastic fibers, which in fact descends from Lepink's model, and so we practically rewrote the model using our current Calgary model by using viscoelastic fibers. So the fact that there is a fluid flowing through the elastic skeleton already makes the response overall viscoelastic, and we know that. So there is an extrinsic viscoelasticity that comes from the fact that the system is biphasic, and so there is a fluid flowing, and there is an intrinsic viscoelasticity because, yes, it's true, the collagen is viscoelastic. So viscoelastic fibers are more realistic than elastic fibers.
I was interested in when you talked about the recruitment of the collagen fibers. I initially thought you were talking about cartilage, but then I saw you were talking about tendon. Do you think in cartilage that might be a possibility as well, or do you think that's very specific to tendon and ligaments?
That actually also happens a lot and is used a lot for blood vessels, in fact, because the collagen in blood vessels, a lot is initially done by the elastin. Elastin is called elastin, in fact, because it's very elastic, whereas collagen has a hysteresis loop. When you load and unload, you see the hysteresis actually. Whereas in collagen, the hysteresis is in elastin, the hysteresis is very small. So when collagen kicks in, it means that the blood vessel is really stretched a lot, and so the recruitment is also very important for this type of material.
Cartilage. Do you think it's important in cartilage, or might help
in cartilage? I think it may be less important because cartilage is pre-stressed by definition. Cartilage is a lot pre-stressed because of the swelling pressure that comes from the interaction of the proteoglycans and the ions dissolved in the fluid. So probably the collagen fibers in cartilage are fairly stretched already. So they are, if not completely beyond the recruitment phase, they have a good percentage of already recruited fibrils, probably.
The other thing that always surprises me is, in your permeability graph, the one that you already showed there, that the permeability, don't go there. The permeability, is so much decreased there in the surface, but presumably because of the collagen fibrillar arrangement. But collagen fibrils are relatively far apart and they leave big pores. And so I'm always a bit surprised about that. Are you surprised by that, or do you think, no, that's the real result? It has all to do with the collagen fibrils.
It is true that they are fairly far apart, but they're also thick. So they take away a lot of cross-sectional area for the fluid to pass.
So you think that's the actual result? There's not something else that might be the.
I'm fairly confident it is. But I have to say I'd be equally happy if these were completely wrong and we would have to start from scratch. That'd be fun. When I get close to retirement, we can come up with a completely different model and say, by the way, we were wrong.
Last question from the FAP experiment with Kotaiba and the diffusivity. Can you relate that to permeability?
Okay, so this initially was one of the things that we wanted to do. So can we relate permeability and diffusivity? So I think that we can, because if the diffusivity is different, in two directions, the culprit really should be the collagen fibers. And so the collagen fibers are also the culprit for the different permeability in the two directions, because we have seen the collagen fibers tend to direct the flow. You know, the flow is easier in the direction of the collagen fiber rather than across. So if not the magnitude of the permeability, at least we can estimate the directions of anisotropy.
Yeah.
And initially that was, if you remember, initially that was the idea. So we try to measure diffusivity indirectly, and then we try to infer from the diffusivity, try to infer the permeability.
Because
that was the dream.
Because if you could get at the absolute value of permeability with FRAP experiments, that would be really neat.
That would be fantastic. But even if we could do an experiment in which we get, even if we get only one permeability value, then we have the ratio, so we can find the other one, for example, in the plane. So that would be already fantastic.
Good. Thank you very much.
Thanks, Walter. Thanks so much.
We're just about out of time, but we'll do our last two questions quickly. Amin, if you would like to go ahead.
Okay, I want to simulate OA progression in my knee joint model. I have like different things to consider. I need to adjust the permeability. I need to take into account that the fact that the collagen fibers gets weaker in the early stage of OA. We have like a different distribution in the maybe like collagen fibers in the OA. So we have different things to consider, but I just want to consider the most significant factor, just one of them. Which one it would be?
So again, on this one, I would also call upon Walter to support me if I say anything completely stupid, but it also depends on the stage that we want to model. So, because early osteoarthritis is quite different from late. So in early osteoarthritis, you don't have a lot of geometrical disruption. So you started to have disruption, particularly inside the tissue. So the collagen becomes weaker, the tissue swells more, so the layer becomes thicker. Consequently, since the mass is whatever it is, the permeability becomes higher because you have less proteoglycans per unit volume, so you have more pores per unit volume. And so that would be my best guess would be to start to weaken the collagen fibers and to thicken the model. So if you have, for example, a swelling model, that will be done automatically. If the collagen fibers are weaker, the model just swells more, and then the collagen fibers keep it a little bit later than they would in the healthy tissue. For late osteoarthritis, then that's problematic because you have disruption. The surface is not a surface anymore; it becomes a fraction.
I was looking for earlier stage, and thank you.
So early, I would say, if Walter also agrees, I would say there will be the weakening of the collagen fiber and the consequent swelling and increasing permeability. That will make a big difference. Thanks, Walter.
Robert, would you like to ask our final question?
I'd love to ask the final question. I was looking at the mid-range where the collagen fibers were very wavy. And at the same time as I'm thinking about that, you just said that the cartilage is pre-stressed. And so I'm thinking, if this area was pre-stressed, why are those areas still wavy?
Bad drawing. It's a bad drawing. So in fact, I was wondering if with the fluorescence microscopy, whether you don't have an image unloaded and loaded, so you can actually see the collagen fibers in that mid region, and do they change from being wavy to being straight as we would expect? So I know that the way in which collagen orientation has been determined experimentally goes with the second harmonic generation, for example. But for cartilage, I don't know if this has been done with second harmonic generation. Walter can tell me more. I think so.
Not really under the microscope loaded, but Clark has done really nice experiments where he flash froze articular cartilage under unloaded and loaded conditions. And then you see exactly the type of behavior in the collagen fibril that you were describing.
So Walter, it does straighten out, and it is, responding to stress in the typical way for collagen fibers.
Yeah, it does.
Yeah, and you've got 3 distinct regions of collagen. Are they the same type of collagen?
It is the same type of collagen. It tends to become, in fact, according to the classical model, in fact, is the same fibers. So they run from the deep zone to the superficial zone, and then they tend to go down. So what we see. Okay, let me go a little bit with order. There is a paper in 2003 by Mollenhauer on connective tissue research. So they used X-ray diffraction for the orientation of the collagen. So what happens is that they see a fairly clear peak at about 0 degrees in the deep zone, 0 in this direction where the angle is 0 with respect to depth. They see fairly 90 degrees in the superficial zone, or a little bit less than 90 degrees. So that's the collagen doing this. And then they see white noise in the middle zone, which means they're random, because they see only white noise. So one way to think about it is that there are these arcades that are made, and then in the middle zone, since the arcades have different orientations, you see these collagens that are passing and curving and so on, and you see a random orientation when looking from a set direction. So that's the best way that I have to think about.
Right. Thank you.
Thank you.
But Rob, you're right. It's essentially type 2 collagen everywhere.
Is it?
So type 2 collagen, in the extracellular matrix, and then in the pericellular matrix, in a couple of special issue, you get different types of collagen. But the basic collagen, the most collagen that you see from top to bottom, is all type 2.
Right.
And what changes is the thickness. For example, there are more fibrils that make up a fiber in the deep zone, so the fibers are thicker.
Yeah.
And in the superficial zone, they tend to create a little bit of sheets. There are sheets of collagen. That's why, for example, the fluid flow is difficult in that direction too.
Thank
Great.
you, Salvatore.
Thank you. Thanks.
Salvatore, thank you so much for your presentation, and everyone in the audience,
Thanks,
thank you for asking some great questions. As a reminder, we will not have an HPL seminar next week due to the university holiday, so I will see everyone in 2 weeks for the next seminar. So thank you again, Salvatore.
Thank you, everyone. Thank you.